So for demo number 4, it'll be coming from the West Coast, from Washington. Professor Jeff Bond will be taking us through the next use case. Are you there, Professor?
Yes, I'm here, Greg.
Okay, great. Take it away.
Okay, all right. Okay, thank you, Greg, again. Good afternoon. Good morning from Seattle. It's still in the morning time in the West Coast. I've been with the demo so far. It's fascinating to see all the great work facilitated by Mcity 2.0. I'm happy and honored to present the last demo case, which is network level multi-scale signal vehicle coupled control with connected autonomous vehicles. I hope this is pretty clear from people working in transportation as we see the massive development of autonomous vehicles and connected and autonomous vehicles. We sort of project the future sort of large-scale deployment of those vehicles and technologies. As a transportation researcher, I always, not always, but in the last 10 years, been, trying to say how they can work with the infrastructure that, with the infrastructure support, cooperative, working together to really magnify the benefit that those technologies can bring to us. So one of the test case we've been working on is, when they drive on the urban streets, how they can work together with traffic light, for example, to share information, to control the vehicles, more kind of coordinated way, so that it can improve safety, enhance mobility and other objectives. So this is the work we've been working for the last 10 years. I'm glad to. So today, this is actually, I also wanted to first introduce the team, really by 2 PhD students with the support of many other graduate and undergraduate students. So Dr. Changchang Guo, who was a PhD student in my lab and graduated about 2 years ago, now working in the industry, but he was the first person who sort of developed the models and also the first version of those control algorithms. So he's still supporting us, for the demo and other aspects. And also Sakiba Nadarin, who is a 4th-year PhD student, has been working on this topic and project for the last 3+ years, mainly extending the work of to network level control, multimodal, which I'm just illustrating a little bit later, and particularly try to extend from simulation to the field testing and the testing with Mcity. What we actually do, right? So, for the last 10 years, as I mentioned, on our side, we've been particularly developing this we call multi-scale signal vehicle coupled control, SVCC, models, algorithms, some of the theories and computation. That's including mainly vehicle control, how to control signals, and how to combine them together in this so-called MPC scheme and maintain consistency, because you have vehicle level control, you have signal level control, how you make consistency when you control both of them, right? So we've been working on that, and then we've been mainly testing and do the sort of experiments unit simulation that you can see here. We did that in the Seattle area, the downtown Seattle. We have a simulation network. We also tested it on the Mcity network, but everything in simulation. Then we also, we know we have this great Mcity test facility with all the kind of real world facilities and the scenarios, but it's conventionally it's really hard to access for us at least, right? So you have to travel, you have to sort of sometimes bring your vehicles and bring your personnel over there. So thanks to the Mcity facility, they particularly developed this TerraSim API interface, which is really a cloud-based remote access facility, so that we could now try to test our algorithms on their facility. Essentially, they can send their vehicle infrastructure status, particular signal status, to the UW side, and on our side we can use this information and to run our models, algorithms, and send the vehicle and signal control command to the field, and the signals and the vehicles will be controlled using our algorithm. So this is how this is done. So today we illustrate, how the remote kind of control can be done. So I'm presenting the slides from my house. Sakiba, who will momentarily sort of show the demo with the Mcity engineers and researchers from the lab. We actually tested this earlier last year and demoed this for one intersection, as I show here. So today, the focus is mainly on, we call network, actually 6 intersections that you can see from the right figure. We control this 6, and we control the vehicles going through those. We tested in both simulation and the mixed reality environment of Mcity. So in the simulation, we test different penetration of CVs, and in the mixed reality testing, we have one CV will be controlled by our algorithms. All those CVs will be controlled by our algorithms. And also, for the 6 intersections, their timing will be controlled by again by our algorithms. So will be not shown in this demo, but we are also working on the multimodal traffic. Like when you have pedestrians and cyclists, it's a multimodal environment. How you can sort of coordinate and ensure safety and mobility of both vehicles, other users, and also the timing is the most efficient. So with that, I show the simulation performance that you can sort of see on the left side. We have, if all the vehicles are CVs, then as you can tell, the left kind of bar is our algorithm. That's sort of, because we are assuming fuel consumption, lost time, and queues, the lower the better. So we can see the performance is normally outperforms the conventional signal control algorithms, and this so different penetration how the performance changes. Again, this is in simulation, and I'm looking forward to see the actual field testing, and we'll report the performance later on. So with that, Greg, I'm done. I'd be happy to take questions after the demo. Thank you.
We will take questions after the demo. There's going to be a live demo here, so don't want to interrupt the timing there. So thank you for your interest, though.
So Kiba, I think you're muted. So
yes. Hello, everyone. To give a brief overview of what's going on during the optimization at each time step and for each of the 6 intersections on the Mcity network, the multi-scale SVCC model will first collect real-time data on the current intersection condition. This includes the position, speed, and waiting time of all the approaching vehicles into the intersection, as well as the signal status at that current step. This information will then serve as input to the SVCC optimization module, which generates an optimized plan for both signal states and vehicle trajectories over a 30-second prediction horizon, with the goal of minimizing total vehicle delays, maximizing all the vehicle throughput into the intersection, and reducing total fuel consumption of vehicles that are passing through the intersection. More specifically, the multi-scale nature of the optimization process helps output the optimized signal states at 5-second intervals and vehicle trajectories at 0.5-second intervals to comply with multi-scale safety considerations. I should also mention that for each of the intersections, the solution of the approaching vehicle trajectory points is also being continuously shared with the neighboring intersection. This enables downstream controllers to anticipate future traffic demand, even for vehicles that have not yet entered their communication range, and then incorporate that information into the optimization process of that intersection. Finally, the optimized commands from the model for the vehicle trajectories and signal states will then be sent back to the testbed facilities through the TerraSim API to control both the traffic signals and CAVs on the field for that particular time step. So for example, at this intersection, the one on the right side, the controller detects that all the vehicles on the intersection and turn the eastbound, westbound phase green. So in a way that it would result in the total minimization of the vehicle delay and maximization of the throughput overall. And I think CAV is near the end of its road now.
Okay, I think at this point we will open it up for Q&A. I just want to throw out there that on the right screen you were seeing a bunch of red and yellow vehicles. The yellow vehicles were virtual background vehicles. The red vehicle was our real MKZ on the facility here. On the left is our chase cam that we were using in the earlier demos to show that it is indeed a real vehicle. So with that understanding, I'd like to open it up for questions.
Can I use it? Well, about 55 years ago, I carried out some research on traffic lights where we introduced in Israel a phase of 3 seconds of a flashing green indicating the end of the green phase. It means like today you have for pedestrians counting the seconds for how much time is left on the red light for the pedestrian not to go in, or if they started to clear the pedestrian crossing. And the idea was that it was, I think, maybe premature. It was something that started in Canada, in Austria, and in some parts of Germany. And we tried to introduce it. I'm talking about 1970, going 55 years back. And indicating to the driver, look, you are on the green light, yet remember at the last 3 seconds, you got a flashing green. So you know that 3 seconds ahead of you need to make a decision to cross the intersection or to stop before it, you already have some indication. And we wanted to see what is going to be the difference between the situation when you had just the green phase full regularly, and then you got the amber phase in between. That makes you the possibility to go in, clear the intersection if you penetrate it because you couldn't stop on the spot. And I did find out by research of before and after research, that once we introduced the green phase, flashing green phase 3 seconds, the amount of drivers who didn't stop harshly, like in emergency with G over 0.4 and things like that, that it improved the functioning of the braking on the one hand, and then it reduced also the number of drivers that penetrate the intersection on red light, because they were planning ahead. Now I'm asking myself, we come to the days where we have a lot of IE and the possibility of simulation and things like that. Had I carried out that research today, not 55 years back, and then I will take the existing situation with a regular amber phase without a flashing green, and then I would say, okay, I know the behavior of people relative, and now I'm just putting some indicators, anthropological, others that are connected for behavior of drivers when they approach an intersection. And I say, look, I put into the model that I'm trying to do a simulation of drivers who will react according to certain variable criteria that I will set, and carry out the after effect when I introduce the flashing green, not on the spot, but more by the simulator, based on the reference data that I collected and the first phase, which was on the spot, I filmed it. So the question is, do you believe that with the technology that we have today, with the models that we have today, that we can just simulate some other drivers that do the same thing, the same amount of drivers with regular speed approaching the intersection, but yet I put some indicators for them, for variables of behavior. What would they do? Would they stop? Would they accelerate? Will they make an emergency brake? Yes or no? Do you believe that nowadays the technology, it's more methodology of research, we can use these means that you are now showing us about the behavior of drivers once they have conflicts and they have to resolve them, then that we could carry out a research on a before study with the data that will be based for the second phase of the research, but doing the second phase of the research by simulation in the laboratory, not on the spot. It's a very complex situation, but what do you feel about now the methodology of the means that we have in order to really simulate a research, having one phase on the spot, which gives us some ground, and then come back to the laboratory and carry out the second phase of the research? Thank you.
Okay, thank you for the question. I try to answer because it's maybe have multiple layers. I try to take on. So I see two aspects. The first one is when you talking about the flashing kind of 3 seconds green remaining. I don't see that, but I saw in some other countries there are counting down clocks about how the green, like there's 10 seconds, there's 20 seconds. I think it depends on the controller. Some of the controllers may be able to do that, but in the US, this is generally not available because largely use actuated signal. They don't know how many seconds will be you will have because it depends on the actuation of the sensors or the vehicle arrivals, right? So I'm assuming in those countries that you have the counting down clock, that you can study the behavior as you just illustrated. So another aspect I wanted to mention is for this, sort of the model, the vehicle and the signal coupled control algorithm, because we do prediction using the information and the signal timing plan we come up every 5 seconds may be revised. Well, you could have some sort of flashing, but this plan likely be revised. So it's I don't know if that's we haven't I haven't thought about this question carefully. So I don't know if in our model this sort of flashing like 3 seconds remaining green can be done, but that generally I believe is an interesting research question that we definitely can look into that. I hope that answered part of your question.
Is it operating? I do believe that the flashing green, like as we adopted the counting of the seconds for the pedestrian, can really give some indication to the driver. And the question is, will it be on the positive side or be used on the negative side? I'll just end up with some kind of an anecdote from the real life. That I was teaching in a course of transportation safety in Ethiopia. I was going from Israel to Ethiopia to present a course on these issues. And then I was called by the president of the country, whom I knew, and he called me to come over him for just social connection. And then I had a driver. And here we come to a major intersection in Ethiopia, in entrance to Addis Ababa. And it had like 5 branches to the intersection. And then the driver stops. And I say, "Why did you stop?" He says, "I have a red light." Now I was checking, I saw the red light. And beside the red light, there was a counter. And he started to count. 274, 273, 272, and so on. I said, "You mean that we need to wait 270 seconds till the red light will end?" So this is the practice here. So I had on that course, which were prominent engineers, also the traffic engineer. He had a PhD from Delft, from the Netherlands, and he was the chief engineer for the city of Addis Ababa. And he said, look, I experienced something really funny. I saw that red light that has an indicator for the seconds. We were starting with 300 seconds counting down. What about it means? I've learned that you can introduce and put some kind of reducing time and letting the people know, because this is a very major intersection with a lot of drivers, and they have to know how much time they have to spend near the red light. So this is something that really, like you say, that any research or anything that you do in one place doesn't really fit to be implemented in another place. And the question is, do the tests that are carried out at the U of M, Ontry, or in Washington, or in other places, are they valid to draw conclusions? Because the different of cultures, different population, different topography, different kind of thing. So every place has to check their own possibility to implement some new idea. Thank you.
Mm-hmm. Yeah, sure. I think that's a valid point. But with the technology advancement, especially when we talk about autonomous driving, then I think one aspect is to eliminate or reduce sort of the uncertainty on the human side, right? So the issues you sort of raised is, different people have different reaction or behavior with respect to, different technologies. When they're as a driver, they might behave differently. But if you have autonomous driving, of course, we cannot expect 100% very quickly. But when the very large penetration of CVs can be in place, then those kind of uncertainty can be reduced, because the vehicles may be manufactured or designed in a very, similar kind of behavior, or at least not very surprising, right? So kind of predictable behavior, then the systems can be managed in a more predictable way. I think that's sort of my understanding of this aspect. Yeah.
Thank you both very, very much. I'm going to give you another round of applause, because that was pretty.